This map is a map of Great Britain, and we've got the current electrified lines marked up in blue, a few proposed lines as well. But that represents only about 40% of the network. Even with the plans announced, there'll still only be around 50%. So there are vast parts of the nation with no electrification whatsoever. The current alternative is diesel. And there are a number of problems associated with diesels. Carbon dioxide emissions contributed to global warming and climate change. Particulate emissions leading to lung cancer, noise pollution. There are only finite fuel reserves, as I'm sure you're well aware, and I thought I'd get world peace in. Security of supply. If you look at the areas where oil is available, they often correlate with the sources of oil. So a long-term alternative to diesel is needed. Incidentally, as I proceed, I'll be putting messages at the bottom in case you're not sure what's going on. Just read the message at the bottom. So, one solution is, of course, further electrification, but that isn't the solution that I'm looking at today. I'm looking at a solution which is the magic of hydrogen. We should look at the possibilities this element can provide as an alternative to diesel. Now, in case you don't know me, my name's Jeff Allen, and I would like to spend the next 40 minutes entertaining you, and I might just enlighten you as well with the magic of hydrogen. What I want to do is get you thinking away from RSSB, out in the remote countryside at night, looking up in the sky, and what do you see? Well, if it's cloudy, it'll look like that. But if it isn't, you might be able to see the Milky Way. And this is our galaxy, which is filled with an estimated 200 to 400 billion stars. It's difficult to get it too accurate because once you start counting, you forget. The sobering thought is that this galaxy of ours is one of hundreds of billions of galaxies. As you gaze upwards, you may want to ponder on the fact that the most abundant element in the universe is hydrogen. Okay, if we go a bit closer, and I know some of you were looking at this a little bit earlier, the Sun. Our nearest star is the Sun. And again, the most abundant element in our own star is again hydrogen, which generates the heat and light which we enjoy, particularly on a summer's day. So the key message there is that the energy from the sun comes from hydrogen. Getting even closer, planet Earth, our own planet. Now, planet Earth is a notable exception. The most abundant element on Earth is not hydrogen. Does anyone know what the most abundant element on Earth is?
Carbon.
Sorry? Carbon, no. No. No, I'll tell you, it's oxygen. Fortunately for us. So oxygen is the most abundant element on Earth. Now, what I want to cover next is key to the whole presentation. It's the magic formula. And the magic formula goes something like this. We add hydrogen to oxygen, and it won't come as a surprise to many of you, particularly the chemists on the front here, but what you get is H2O, which is water. What we often don't appreciate is we also get energy. So by combining hydrogen with oxygen, we can produce energy. Now, when I came in this morning, I thought it was a good idea to have a look in the Financial Times. So I bought a copy, and I don't know whether anybody else has... Whoops. Mustn't spill anymore. I don't know if anybody else has looked in the Financial Times today, but there's quite an interesting article talking about climate change on an Arctic voyage opening up to allow ships through the Arctic, and that obviously a shortcut. And it's quite an interesting article, but I wasn't sure really exactly how watertight the argument was. So I thought I'd test it out. Yeah, seems pretty watertight to me. Still watertight. Oh well, there's your magic. Thank you. Okay, let's go a little bit closer in. I want to go to the USA, and some of the older members in the audience might have remembered hearing this.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Does anyone know who that was? Yeah. John Kennedy. Yeah, my neighbour actually worked out who the other two were. I'm not that clever, I'm afraid. Those were the words. I believe this nation should commit itself to achieving the goal before this decade is out of landing a moon on the moon and returning him safely to the world. Year? Anyone? 62. Not far out. It was actually John F. Kennedy in 1961. And it was quite an incredible challenge for such a humble minor country back then, and it would be a major challenge now, I think. So that major challenge was issued in 1961, and it was actually a challenge that what was to become the Apollo moon mission was slightly surprised about. They were hoping for funds, but they weren't hoping for a deadline that was quite that short. So, sometime later, we obviously haven't got the technology now to produce it. Right, well those are the words. That's one small step for man, one giant leap for mankind. And that was the successful mission led by Neil Armstrong in 1969. Now some of you will be aware that there were a number of engineering challenges to achieving that. And this was one of the first ones. Now I've primed Jeff for this, wherever he is, at the back there. Jeff, I'm not going to ask you for the model number. We're going to say this is a 1906A. And you're going to tell everybody who made that.
It was made by a company called ICL, who was the British computer industry at the time. White hot heat technology. These days it probably has about as much power as your average watch, I think. But in the days it was absolutely the sort of trailing edge of, leading edge of technology.
Thank you. Leading edge of technology, and as you can see, it's quite large, occupying more or less a house. This was actually the single computer that we had at the University of Birmingham when I started as an undergraduate. And one of the first jobs that the mission had to achieve was reducing that in size, which they did. And this is the navigation computer, which is not much bigger than a modern desktop. But that wasn't actually the most significant problem that they had to deal with. Much bigger problem was working out how to power the craft up in space for 3 days and support 3 astronauts. And what they did was they looked at the technology available, and that is a modern car battery for a fairly small car. The technology they had available was a little less forward than that one. But what they did was they turned to an area or an application where this type of problem had been experienced for a number of decades on submarines. And they tried with batteries. Now, they weren't very successful with batteries because of basically the size, the number of batteries they would have needed would have been relatively large, taking up a large amount of space. And so they looked at a different technology. And I'm just about to show it to you now. Now this looks like something out of Doctor Who, I suppose, but this was the plant that they used on board the spacecraft, not only to generate power, but also to generate their water supply. And what they did was they carried hydrogen gas and oxygen gas on board the spacecraft, and they used what's called a fuel cell, this device here, to produce power from hydrogen and oxygen. And it's a fairly straightforward device. It's got a couple of electrodes, and basically you pump hydrogen in at one side, oxygen in at the other, and you've got your power and your water coming out. And these devices have been used ever since the Apollo mission, all right the way through the shuttles. The Russians use it, the Chinese use it, and so forth, for all their missions. Now what I've got is, I've got an experimental one here, a little one. This is the fuel cell here. Basically looks like that. I'm going to pass this around, you can have a look. Please don't dismantle it, I've got to use it a little bit later on in the presentation. Now, a couple of years ago, I would have struggled to have demonstrated one of these devices. Commercially available devices anyway. But within the last 2 years, these units have been coming out. So this is a mini pack, a hydrogen fuel cell. That's the fuel cell there. And I've got 10 litres of hydrogen here. I'm going to plug in. Now you'll see the little red light flashing. We've just got to wait a short while that red light turns to blue. So you can keep an eye on that. Be long, I hope. There we go. Right, that's all ready now. So if I put this on, there we go, a hydrogen-powered torch. Now, I've just thought of a brilliant idea. Just happen to have one of these handy. Now, I must apologise for the inaccuracy of the scaling of this model. I didn't have time to paint it either. Now, what if we get a big one of these and put the hydrogen fuel cell in it, connect it up, and then we could have a locomotive. And once that locomotive gets to a particular location to carry out a bit of work, we have a very strong and powerful power supply. So we could use that for lighting the area, for running welders, whatever we need. It's a portable power supply. So there we go. Right, well that's all very well, but there's a slight problem with the technology. Better. Can we do anything a bit more than that? Well, this is the University of Birmingham. This was filmed earlier this year, and it is the UK's first hydrogen-powered locomotive. It even makes the right sounds. Now that's 4 tons of load on that that it's hauling. That's about 100 times more powerful than this device, but still not very powerful. It would hardly even power a kettle. You'd wait an awful long time for your tea with that. So, what about the real world? What about going beyond the experimental stage? Well, this was a video that I recorded in 2007, and it was a trial of a hydrogen-powered bus running on the RV1 route, which runs along the Strand, across Waterloo Bridge, across the river, and then, as you can see here, goes back up Tower Bridge. That trial has now ceased, and we now have the second generation hydrogen buses. So this second generation set of buses are running on the RV1 route now. And in addition, below that you can see the taxis, or a taxi, which is also hydrogen powered, and that taxi was developed in time for the Olympics, and is actually powered by a hydrogen fuel cell that's made in the Midlands, in Loughborough, by a company called Intelligent Energy. So really you can see that hydrogen is being used for transport today. Now, a lot of railway people will explain that it's all very well running buses and all this sort of thing, but the environment's very harsh on a railway and it doesn't always work on a railway. Well, this is an even harsher environment, and this is a mining locomotive that was developed in 2002 in the USA, and this particular hydrogen fuel cell is about 10 times more powerful than the one for the University of Birmingham railway. But nevertheless, I appreciate that this is only a small railway and big railways are quite different, aren't they? So, if we now have a look at this. This is 2006 in Japan, and this is the experimental one that was run by Japanese Railways as an experiment. And if you don't think that's big enough, what about this one? Now, the great thing about hydrogen locomotives is they're very quiet, which is why they have to have an awfully loud bell on them. This one is a very powerful locomotive. It's a shunting locomotive. It's a 1 megawatt locomotive, and not only was that proved in terms of trials of shunting wagons around, it was also used as a power supply to supply a complete army base. So there's lighting, heating, cooking, air conditioning, and the US Army were particularly interested in this development and sponsored some of that work. Okay, so as you can see, it's a little bit more than just a fanciful idea. It's something that seems to work. And what I want to do now in the remaining time is progress on to look at two elements of hydrogen. One is manufacture of hydrogen and production of hydrogen, and the second thing is storage. So let's have a look at manufacture. Well, what I need is a chemical plant like this, and obviously I can't bring that into the presentation. So you just have to pretend. No. There are other ways of doing it, so we'll have a go at one of those. who left this line there? Now, all you need is some water, bit of plastic container, a few LEDs, a couple of AA batteries, got some of those over here, a syringe, I will need that device back wherever it is. Yeah, so hurry up now. Okay, so we'll put the. Can you all see that? Whoops. Bit too much water in there. What pretty lights. The lights are completely irrelevant. They're just done to improve the presentation quality. Now, I don't know whether you can see that, but the lights don't help, but there are bubbles of oxygen appearing there, and there will be hydrogen pouring out there. Has somebody got the... Thank you. Now, I just need one of these. I just happen to have down there. Right, there's absolutely nothing there at the moment. So what I'm going to do is just connect this supply of hydrogen . Well, there it goes. There we are. So we're getting that hydrogen produced. It's going into the fuel cell, and the fuel cell is now generating a small voltage. We'll give it a little bit longer. Get some time to get going. Actually, I could make it a lot easier by pulling this out. There we are, nearly a volt. And if you string these all together, you can get the sort of thing to power a locomotive if you make it big enough. So, that's a means of producing hydrogen from water using electricity and then feeding it into that fuel cell to make the fuel cell work. Can I advise anyone who's thinking of presenting to the whole of RSSB and doing live demonstrations? Probably not a good idea. Okay, well there are a large number of ways of producing hydrogen. The way that it's often used these days is from natural gas, but there are more sustainable ways of doing it, although even from natural gas you can get some advantages. This was a slide that I produced 5 years ago when I last presented on this subject, and this part hasn't changed very much. Electricity applied to water, get some hydrogen as we've seen. and then you can apply it to any of these more modern forms of transport. I had 3 examples in there in the last presentation, and each one of those has been replaced with a more up-to-date version. So things are progressing here. So sustainable electricity is able to produce a portable fuel, and if you use the sustainable electricity, you get no carbon dioxide, no noise, no particulates, etc., etc. Now, what I want to move on to next is to looking at how we store hydrogen, because having produced it, you can't always use it directly as we have here. And one of the most popular ways in which hydrogen is stored is by compressing the gas. And this is the technique that's been adopted by a number of car manufacturers, and we will be seeing these cars, I suspect, in the next couple of years appearing. There's a lot of money behind producing these. That compressed gas then goes into this type of cylinder, which is typically made of carbon fibre with a polymer inside, very robust form of storage. There is quite a bit of nonsense that's talked about storage of hydrogen using compressed gas. One of the myths that goes around is that you put a lot of energy into compressing the gas. Well, to give you some idea, it's about 5%. So the energy that's in that gas, if you want to compress it to a reasonable extent to go into something like that, you use an additional 5%. There is a way of getting a longer range that I want to talk about next. So this is the most popular form of hydrogen storage. But what I want to talk about next is liquid hydrogen. But I want to give a little bit of background on that, because if we think about temperature and start at 110 degrees centigrade, so this is 10 degrees higher than the temperature that water turns into steam, it's in gas form. We have hydrogen gas at 110 degrees. If we go down 10 degrees, we've got water in the form of gas, i.e. steam. If we go down a further 10 degrees, we've obviously got liquid water. And if we go even further down, get down to 0 degrees, so we're now at ice temperature, it's still a gas even below that, minus 10 degrees. So let's keep going. So get to minus 80, it is still a gas. Just to give you some idea, minus 89 degrees is the coldest recorded temperature in Antarctica. Right, we'll go down a lot quicker now and a lot further. At minus 240, we still have hydrogen as a gas. We actually have to get down to minus 260 degrees centigrade to get to liquid hydrogen. And to give you some idea, the very coldest temperature that you can get to is minus 273. It's not physically possible to get below minus 27, or approximately minus 273. So that's how close liquid hydrogen temperature is to absolute zero. So to put it in simplistic terms, liquid hydrogen is very, very, very cold. In case you're wondering, liquid nitrogen, for instance, the equivalent temperature is minus 196, which is much warmer, and it actually freezes at minus 210. So this is really, really cold. So which car company in their right mind would attempt to store liquid hydrogen? Well, the answer is, of course, BMW. And BMW have come up with a couple of cars. This is one of them, and this is the... they always use these LED lights. This is the tank in the back, partly in the boot and partly on the rear shelf. You can see what it's like in the boot. And this is like a super thermos flask for liquid hydrogen. This requires quite a bit of more energy, but even that is only 25% of the energy that the liquid hydrogen holds. And it does give a great range. And you can see here one of their minis being filled up with liquid hydrogen. So it's a great range, but there is an energy cost to it. So what I want to move on to is another technique which is used. And that technique is of particular importance to us. Now, I will have difficulty in doing much in the way of demonstration of this, but I'd like to give you an analogy, and I've got my analogy here. So we've got a sponge here, and you could obviously use that to soak up all the water I've spilled during the presentation. And then to release it, we can squeeze it and all the water comes out. And there's a particular type of compound, metal hydride, which I've got in here, which is capable of absorbing the hydrogen if the hydrogen is presented to it. And then it can be released with a very modest amount of heat. In fact, so modest that the hydrogen fuel cell I showed you earlier, which I seem to have lost, oh, it's over here, using this cartridge. And I'll pass a few of these round. Is filled with metal hydride. So these cartridges are filled with metal hydride. The hydrogen is presented to them, and this means they're not pressurized. These are not pressurized at all, and in fact you can carry these on an aeroplane. I'll pass these around. You can have a look. Please don't take them apart. One there, one there, and one there. Now, how much hydrogen have we got in there? Well, we've actually got really quite a lot. That's 2 litres. 4, 6, 8, 8 and something else. 9, 10. So that little cylinder that some of you are holding has got 10 litres of unpressurised gas in that. And this particular technology is quite an interesting one. It works on the principle of this molecular structure for the metal hydride and the hydrogen molecules or atoms hiding inside the gaps between the molecules. And this actually manages to store hydrogen at a better rate or in a smaller space than current forms of compression. So no compression involved, so there isn't any energy to compress the gas. There's a very low seepage rate from the rupture of the tank. If you were to put a hole in that, it would, because it's not pressurised, it would come out at a very slow rate. And in fact, this form of storage has been used in all the mining locomotives where safety is paramount. It's potentially more compact storage than even liquid storage. It's pretty good at the moment, but it is open to nanotechnology development to make it even better. As I said, no compressing energy or liquefying energy needed. The real problem that you may notice as this thing goes around, it is quite heavy. It's got metal dust in it, in tubes. So it's too heavy for road use. The car manufacturers and the bus manufacturers have found that they can manage quite adequately with compressed gas, which is a cheap way of doing it and perfectly adequate. But rail is an application where this could easily be a very good way of storing the hydrogen. So metal hydride storage provides excellent range because it can store so much hydrogen, and it has a number of safety properties which are particularly attractive. So, in conclusion, this is where the bullet points are, in case any of you have been a bit anxious because you like bullet points. Hydrogen is a portable fuel. Hydrogen fuel cells are clean, quiet, and can use sustainable energy sources. This could provide an alternative to oil. I've also introduced you to metal hydride storage, which has excellent safety properties, and it has already been quite extensively used in rail, and could well be something that's worth pursuing even further, perhaps on the main line. So what about next steps? Well, RSSB is continuing to monitor developments worldwide, and David Knights' team are particularly active in doing that. And we inform the railway industry through a group that you might not have heard very much about, the Future Energy Technology Group. But what can you do? Well, what I would advise you to do is look up in the sky when you get an opportunity and away from artificial light, and just ponder the amount of hydrogen that's out there. The other thing that you might like to do is explore the RV1 route. Now, not all the buses are hydrogen. You might have to wait for one to come along and miss a normal one. You can't miss them. They've got hydrogen written all over the buses. I think I'll work with Diana, and we'll send out a little map of the RV1 route so you can work out where the most convenient place is to catch it. Well, I'd like to acknowledge some of our friends out there who provide us with the information on what's going on in the rail world and other worlds in respect of hydrogen. Vehicle Projects Inc., that we have a very close relationship with. Air Products here in GB. Japanese Railway, the Railway Technical Research Institute, and the University of Birmingham. And one final thought. When you go to Trafalgar Square, you'll see there's a Christmas tree there. In 2004, the lights on the tree in Trafalgar Square were lit by power from a hydrogen fuel cell. And I believe last year, the star at the top of the Christmas tree was lit by hydrogen power. I don't know what's going to happen this year. Maybe it still will. Anyway, with that, thank you very much for your interest, and I welcome any questions you might have.